Welcome to another podcast. In this episode, we're going to be taking a look at an application of integration to physics called center of mass. Now, you're probably familiar with this concept on a sort of a basic level. I want to sort of reinforce that with the first couple of examples that I have here. We're going to start by looking at a very simple figure. Want to look at a rectangle here that were defined on the interval from A here and B here. So it's got area A times B. And if we were to assume that this was some sort of metal plate or something like that, and the plate had a uniform density, then we would know that the place where this plate would balance most easily is at its center. And it's very easy to find that center in this case. This would be the point A over 2, B over 2. We would call this point the center of mass for the plate, or a lot of books will call it the centroid. So that's what we want to do generally, is come up with the formulas to be able to find the center of mass for objects that aren't nice and symmetrical like this. One of the things you'll learn is that centroids must lie on the axis of symmetry for a planar region. So if we have a region in the plane, a two-dimensional region such as this, then the centroid must lie not only on one axis of symmetry, but on every axis of symmetry. And here it's really easy to see that we have two axes of symmetry for this figure, and that the centroid lies at the intersection of those two. Now, if our figure's not quite as nice and neat, then we need a better way of describing how to locate the center of mass, or the centroid. And that's what we're going to look at in this video. I do want to give you another sort of simple explanation of what's going on here by considering just sort of a line here that is balancing on a point, which we'll consider that point to be the fulcrum. And it doesn't have to be, the fulcrum doesn't have to be in the middle. It depends on if there's any objects lying on that line. So let's put a couple objects on there. I'll call this object x1. Then we'll have an object that's sitting closer here at x2. Maybe an object further away here at x3, and then one over here at, let's say, x4. The point is, each of these objects would have their own mass. So I'll give this object mass 1, mass 2, mass 3, and mass 4. And one of the things you know is that the fulcrum is located wherever the average, the weighted average of these points occurs. So for example here, x bar is equal to m1 x1 plus m2 x2 all the way up through m3 x3. And then finally we've got the fourth point. But you have to take those and divide by the sum of the masses. So this is an example of a one-dimensional center of mass. So this is a one-dimensional center of mass. And the calculation of that involves what are called the moments. So these individual pieces are called the moments. They measure the torque about the origin for the system. And then the m's themselves are the masses. And the x's are the positions of the masses. And what you notice here is that the formula for x bar is simply an average, and it's a weighted average. Maybe a better way to describe it is, in general, what you have is the center of mass is described by the sum over all the moments of the system divided by the sum of the mass of the system. And what you notice is if all of the mi's were 1, then this formula is simply just the sum of the data points, which are the positions, divided by the number of points, which in this case would be n. This is nothing more than an average, which means that this is nothing more than a weighted average. And that's all the center of mass really is a weighted average. Now I want to change my picture up slightly, so rather than look at this nice and neat rectangle, instead I'm going to look at a more general region. So let's suppose that we have a function f of x and another function g of x. And together they are bounded between x equal to b and x equal to a. So this is the region R that we're interested in. Suppose I wanted to find the center of mass of that region in general. How would I go about doing it? Well, I want to concentrate on a rectangle. And on that rectangle, I want to locate the rectangle's center of mass, which we've already found that we can do really easily. We know how to find the center of mass of a rectangle. And let me just call that center of mass, let's just do x sub I. And so the idea is I'm going to partition the interval from A to B into a bunch of rectangles just like that. And for each rectangle, I'm going to associate the rectangle with a single point, which we would consider to be a point mass. And so I think of each rectangle as having its mass centered at its centroid only. And the idea is I then will calculate the center of mass in much the same way that we're looking at here. However, I've got to consider both the center of mass along the vertical as well as along the horizontal. And this leads to a little bit of a complication for this problem. So if I could basically summarize here, the center of mass is the moment of the system divided by the mass of the system. So let's see if we can put that into practice. Okay, so let's start off by trying to find the x-coordinate of the center of mass. So the x-coordinate of the center of mass would be described by the formula I have above. Moments of the system times the points xi divided by the sum of the masses. And so the question is, how do we find the masses? Well, in any system, we know that there's a law that relates the masses to the density and the volume. So for this particular problem, the masses would be rho. And what is the volume? So I'm looking for the volume of this piece. Well, the volume of that piece is simply going to be the area of that piece times any sort of width that it might have. And so in this particular case, what you're looking at, it would be the height of that particular rectangle would be f of xi minus g of xi. And the width of that rectangle would be delta xi. And then the formula says times xi. So all of this right here is a description of the mass. And then I would just repeat that for the bottom piece. So I'm just replacing the mass here. And the idea is if we let the number of rectangles go to infinity, so we're looking at decreasing delta x sub I, then we're looking at a limit here. So if I let the limit as n goes to infinity, these turn into integrals. In particular, the integrals of the top would be the integral from a to b of rho times x sub I becomes x. So remember, rho here is the density. And then the width here would be f of x minus g of x. And then delta x becomes dx. Similarly, for the denominator, we would just have rho times f of x minus g of x. And what you see is the rho, if it's the same, if it's uniform, then they would disappear from the problem entirely. And if we do a similar thing for the y's, let me clear up some space here. If we do a similar thing for the y component, then the y component would look like the sum I goes from 1 to n of the masses or the moments, these are the moments, yi divided by the sum of the m i's, which this one's a little bit more complicated. I'm going to replace the mi by the exact same thing that I had above. So this is rho times f of xi minus g of xi. But the y component in this case is going to be described a little bit differently because the x component is just located along this axis. That's easy to find where the x component of each center of mass is. But the y component of each of the center of masses is halfway between the top and bottom of the rectangle. In this case, what that relates to is it's 1/2 of, it's the average of f of xi and g of xi. That's the average that takes place there. And then this would be times the delta xi, just like we had here for that piece. Then on the bottom, this would become the sum I goes from 1 to n of the mi's would look exactly the same, be rho of f of xi minus g of xi delta xi. Now, if I take the limit as n goes to infinity of this, I get more and more rectangles. Look what happens. I have a difference of squares that are factored here. The rows would cancel. This would leave me with the integral from a to b of, on top, if the rows canceled, I would have f of xi squared minus g of xi squared. So you can see that comes from that piece. And then I would have the 1/2, that's a part of the problem. And then the delta xi would become dx. And on bottom, it would be the same integral over here that I have for the bottom. So this is just following the formula that we outlined here for what the center of mass would look like, being the moment of the system divided by the mass of the system. Using that, we've calculated both of the coordinates for the center of mass. If I take this one step further, make it look a little bit better here. Then our result is that x bar is equal to, well, if you look, in the bottom here in the denominator, this integral is the integral that defines the area of the region. So the area of this region in red is the integral that I have on the denominator for both x and y. So I'm going to call the area of this region A, and in which case if you look at the formula for x bar, it's 1 over A, take the area of the region, and multiply it by the integral of A to B. In the top, it's x times f of x minus g of x. Now we've looked at another integral formula this semester that looks very similar to that. In particular, this should remind you of the expected value, or mean, of the distribution f of x minus g of x. In other words, it's looking at all possible x points that we could have in that region, and it's averaging them. And that is, once you divide through by the area of the region, that then averages the x value over the region. And so the idea is that will provide the center of mass, the x-coordinate of the center of mass. Similarly, the y-coordinate of the center of mass is 1 over, you see we've got the 1/2 term here. So it'll be 1 over 2a, integral from a to b of, and if you look at what's left over in that piece, it's the f of xi, or excuse me, f of x. I don't need xi's anymore down here in this formula. So this will just be f of x and g of x. It's the f of x squared minus g of x squared. So you may or may not remember these formulas or how they were derived. I hope what you get out of this is you kind of understand the process here behind this. But you do need to know both of these integral formulas that were produced. These are the formulas for the centroid of the region R that's described in this picture. So if you have an arbitrary function f and arbitrary function g, this tells you how to find the centroid or the center of mass of that region. All right, thank you for watching.